Let's talk about vectors. A vector is a line segment with a fixed length and fixed direction, but no fixed starting point. The book uses A, but sometimes we'll write A like this in class because realistically, who wants to have to write a bold A over and over and over again? For example, this is the vector 1, 2 because it goes 1 unit right and 2 units up. We say that 1 and 2 are the components of the vector. The book uses this notation. So they'll have the v1, v2 in parentheses, but we will use this notation, the v1 and v2, in pointy brackets because it's less confusing, less ambiguous. We could just as easily represent it like this with square brackets or like this. Okay, this would be a row vector. This would be a column vector. We could represent it that way too. Vectors have no fixed starting point, so this is also the vector 1, 2. Or I could have done it like this. This is also the vector 1, 2. Same thing with this. Sketch the vector 3, negative 4. Well, we could have started it anywhere. This is where I started it. Let A equals 1, 2, B equals 3, negative 4. Find A plus B. We add vectors component-wise. A plus B, 1, 2 plus 3, negative 4. It's going to be 1 plus 3, 2 plus negative 4. In other words, it's going to be 4, negative 2. Here's what this represents geometrically. If we put the tail of 3, negative 4 at the head of 1, 2, okay, so here's 1, 2, and here's 3, negative 4. If we put the tail of 3, 4 at the head of 1, 2, then 1, 2 plus 3, negative 4 is the vector from the tail of 1, 2 to the head of 3, negative 4. The red vector is the sum. When we're dealing with vectors, ordinary numbers like 12 are called scalars. We can have scalar multiples of vectors. For example, A is 1, 2, B is 3, negative 4. Calculate and sketch 2A. That's a scalar multiple of A. 2A is 2 times 1, 2. In other words, it's 2, 4. Notice that 2A is twice as long as A and points in the same direction. So, yeah, it's going to be twice as long as A and pointing in the same direction. Calculate and sketch the opposite of A. Opposite of A looks like this. Opposite of A is negative 1, 2, so it's negative 1, negative 2. Notice the opposite of A is as long as A and points in the opposite direction because A pointed in the other direction. So A was like this. Calculate and sketch A minus B. A minus B is going to be 1, 2 plus the opposite of 3, negative 4. In other words, it's 1 minus 3, 2 minus negative 4, negative 2, 6. The red vector is the sum. But here's a more helpful way to think of this geometrically. If we put the tails of A and B at the same point, then the vector from the head of B to the head of A is A minus B. Okay, so here's the head of B, here's the head of A. The vector from the head of B to the head of A is A minus B. And why is that? Because B plus A minus B is A. Okay, so here we have B plus A minus B equals A. We've been dealing with 2 dimensions. Let's talk about 3-dimensional space. Here's how we'd graph it. The x-axis coming out at you. Graph the point 2, 3, 4. There are a couple of ways to do this. You don't want to graph it like this. Where is that? What is that? That's useless. Instead, graph a box. So here's how we graph 2, 3, 4. You start here at the origin. Okay, 2 units in that direction. 3 units out like this. And then 4 units up. Okay, I'm making a box. All of these sides should appear to be parallel because they are parallel, right? And then the corner that's opposite the origin, that's going to be where your point 2, 3, 4 is. So that would be the point 2, 3, 4. See, isn't that better than what we graphed a moment ago? We can also have 3-dimensional vectors like 2, 3, 4. Sketch the vector 2, 3, 4. That's just the vector from the origin to the point 2, 3, 4. So there it is. That's the vector 2, 3, 4. We can also think of a 2D vector as an ordered pair of real numbers and 3D vectors an ordered triplet of real numbers without any reference to geometry. In fact, we can have n-dimensional vectors, x1, x2, x3, ... x sub n. It's just an ordered n-tuplet of real numbers. How do we know if u and v are parallel? Two vectors are parallel if one is a scalar multiple of the other. Two vectors p and q are parallel, in other words, if p equals kq for some scalar k. Are 6, 4 and negative 15, negative 10 parallel? Well, again, there's our definition of parallel. These are indeed parallel because negative 15, negative 10, okay, is negative 5 halves. It's a scalar times 6, 4. So those two vectors are parallel. Is there a vector parallel to both 1, 2, and 3, 4? We'd have to yeah, can we do that? Can we find such a vector? Oh yeah, 0 is parallel to every vector. Here's some vector laws. Let u, v, and w be vectors. Let k and l be scalars. We have commutativity, u plus v is v plus u. We have associativity, u plus v plus w is u plus v plus w. U plus the 0 vector is u. U plus the opposite of u is the 0 vector. And then we have these distributive properties. K plus L times U is KU plus LU. K times U plus V is KU plus KV. Oh, and we have some more vector laws. So K times LU is KLU. It's like associativity of multiplication. The scalar 1 times U is U. Scalar 0 times U is the 0 vector. K times the 0 vector is the 0 vector. And the scalar negative 1 times U is the opposite of U. W is a linear combination of v1 and v2 if w equals c1 v1 plus c2 v2 for some scalars c1 and c2. This is a really important definition. We'll use this over and over and over again. For example, 3, 4 is a linear combination of 1, 0 and 0, 1 because 3, 4 is 3 times 1, 0 plus 4 times 0, 1.